In this video, we are going to work with something called the unit vector. So a unit vector is exactly, we defined it, I think, already in the section. A unit vector has a length of 1, but we're going to talk about how do I find a unit vector. So to find a unit vector, okay, one thing I do want to talk about, when we did v, we would do a vector over that. If I do a unit vector instead of doing the boldface, what we do according to our book is we put a hat. The hats mean unit vectors, and the vector on top of v is a vector. So if it has a hat like that, at least for my class, it means that it is a unit vector. Now, this may change to your physics class. I think I talked to one of the physics professors here, and he uses this, I think, for almost all vectors. You just have to know what your professor wants. I like the hat for unit vector, so we'll go with that. How we do this is I take my vector v, and I divide by its magnitude. And that gives me a unit vector. Another way to look at it is like this, and that'll make sense the more you do it. You'll understand why they defined it that way. But to find, if you're given a vector and we want to find the unit vector, find the magnitude and divide every component by that magnitude. All right, let's, this is called the normalization of v. Remember, we called the magnitude norm. So let's find a unit vector. Okay, find a unit vector in the direction of that and verify that it has length 1. Okay, so the first thing we're going to need, I have v, so I'll just write down v. I like to rewrite things. -4, 7. I also need the magnitude of v, which is the square root of the squares of the components. So this is equal to the square root of 16 plus 49. All right, 16 plus 49, that would be 65. Yep, so the square root of 65. Now we want to find the unit vector. So if I want the unit vector for this, I take v and I divide it by its magnitude. So v is -4, 7, and I'm going to divide it by the square root of 65. Now, that other definition they wrote, they did it this way. And the reason they did that way, we can leave it like this. This is a great answer. I could distribute the 65 and have, I'll do it here just in case, but we don't have to. -4 over the square root of 65, comma 7 over the square root of 65, right? That's what that C said thing above. They want us to verify that it is a unit vector. So that means I need to take the magnitude of that vector and show that it's 1. So it's the square root of -4 over 65, square root of 65 squared, plus 7 over the square root of 65 squared. All right, inside we get 16 over 65 plus 49 over 65. That is the square root of 1, which is 1. So we have verified it. So how we find a unit vector? Find the magnitude, divide by it. If you want to check, you just take the magnitude, make sure it's 1. Okay, we have a little bit more to discuss for this video. Very little. Generally, the length of two sums of vectors is not equal to the sum of their lengths. And it can be. But for the most part, it's not. So take a look at our picture. We have u, and we have v, and then we have u plus v. One thing I want you to notice, a couple things. U plus v is bigger than v. We agree, right? U plus v is bigger than u. But if I add them together, and you can see this, if you think about walking from, say you had to walk from here to here, the shorter path is straight to it, right? So that's where they come up with this. This is called the triangle inequality. Mathematicians in this course, you guys will see this a bunch. You'll have to prove it a bunch. It'll keep showing up. Physicists and engineers, I'm sure it comes up, but we mainly use this for proofs. So the triangle inequality says this. Take the magnitude of u plus v. That is less than or equal to the sum of the sides. Now remember, the magnitude means the length, right? So the length of this thing is this thing here. Right, and then the length of this side, that's magnitude of u, right? The length of this side is the magnitude of v, the length. The u and the v themselves actually don't play a part in the length. They're just the direction, and there is a length, but if I want to find the length, I have to take the magnitude. And then when we're dealing with lengths of triangle sides or any kind of side, I have to have the length of it, not the vector itself. So that's why we get the magnitude bars there, because it actually defines length rather than just the vector. Okay, so we get equality though if they're in the same direction. This makes sense. If they're in the same direction, they would lie right on that line that would connect the straight distance. All right. So that's it for this one.